Evaluate the Riemann sum for the function f of x equals x cubed minus 6x, taking sample points to be the right endpoints, and a equals 0, b equals 3, and n equals 6. So they've given us information here about where our interval begins and ends, and they've told us how many intervals there will be. All right, so let's just make a list of the things that we know. So without really guessing at what this function looks like, I've just kind of sketched a graph here. This might help us visualize what's going on. I know that I've got 6 intervals here, which is why I've got 6 marks on my x-axis ending with 3. So I can divide these up equally, and this would be the 1, that would be 2, right? 2.5, 1.5, 0.5, etc. This just helps us visualize what's happening here. And so we've got some intervals that go from 0 to 0.5, 0.5 to 1, 1 to 1.5, and so on. And we're estimating, or we're approximating, the area under this curve, which we're going to represent as a right-hand sum of 6 intervals. And I'm just going to write that using our right-hand sum notation. We're starting with 1 and ending with our 6th interval. And since it's a right-hand Riemann sum, it's f of x of I times whatever delta x ends up being. And so we know that delta x is going to be 6 minus, or rather 3, minus 0 divided by 6, which is 0.5. That makes sense because all of these intervals have a distance of 0.5. And now we can apply this to the idea of actually calculating here. All right, so how are we going to calculate the height of each of these triangles? Well, I don't necessarily know exactly what this function looks like. I don't know without graphing it if these rectangles begin going under the x-axis or if they begin by going over the x-axis. I'm not really sure what the behavior of this function is, but I know that whatever it is, I'm going to have either something like that, or maybe it's downward, right? Whatever the case may be. Still, that doesn't change the fact that the way that I'm going to calculate the area of that particular rectangle is going to be the change in x, that's the width of the rectangle, times f of xi, or x1 in this case, which would be 0.5. So that's just that first rectangle, right? Times, or plus delta x times f of x2 plus delta x times f of x3, and this continues until finally we add delta x times f of x6. And so these are some calculations that we can actually make, but to make those calculations easier, I'm just going to recognize that there is a delta x in each of these terms, so I can factor that delta x out. So this is going to equal delta x times f of x1 plus f of x2, etc. All right, so let's just calculate those values then, and I'm going to use the actual function to plug those numbers in. So what is f of x1? Well, x1 is 0.5, so I actually need to plug in 0.5. And when I do that, I get negative 2.875. So by plugging in that first value, I'm recognizing that this function actually is beneath the x-axis during this time. So I am getting some negative area from this first rectangle. But that's represented here by the fact that this is a negative number. So we're in good shape. All right, now I need f of x2. And x2 is 1. So I just need f of 1. In this case, that's negative 5. So I've got another negative number. Looks like our function is still negative there. I'm just going to plug the rest of these values in, continuing on along the same pattern. So I've got all my values calculated here. Notice again I did replace delta x with 0.5 because we know that the width of each of these rectangles is 0.5. And so now I can finally calculate the sum of everything that's in here. Notice this will take care of that net area problem that we discussed in previous lessons, because some of these areas are negative. Those are the ones where my rectangle would be below the x-axis, and then some of these are positive. So depending on whether my positive or negative values are heavier in this calculation, we may end up with a negative or a positive net area. But when I actually evaluate that, I have negative 3.9375. So that ends up being the sum of all the area between the curve and the x-axis. And notice we're getting a negative number, which must mean, if I sketch this thing in here, that we've got a shape of this curve that's, I don't know, something like this, where it's coming down, and we've got some negative areas. But then right around here, it gets positive because we do have some positive values for areas of these two rectangles. So this rectangle here and this rectangle here would be positive, but the others are negative, and obviously the negative rectangles are overpowering the positive rectangles, so we get this negative value. So negative 3.9375. And so let's take the same example and discuss the way that we would handle this if it were written in integral notation. So if the question were presented this way, we would still need to calculate delta x, but this time it's going to be 3 minus 0 over n, and we don't know what n is because once we're using the integral, then we're sort of taking the limit as n approaches infinity. So this lands us with 3 over n as our delta x, and we've stated that we would represent xi as whatever our a value is plus I times delta x, which in this case would be 0 plus I times 3 over n. And so that would just be 3I over n once we simplify this. So we could say that this whole expression could be rewritten as the limit as n approaches infinity of the sum from the first to the nth term of f of xi times delta x. But we know that this is x sub I and this is delta x. So I can replace those values with the values that we calculated earlier. Now I'm going to actually evaluate f of 3i over n, and I can plug in 3i over n into my function. So I've just evaluated f of x, or this function here, but replaced x with 3i over n. And now remember that I is our variable here in where the sum is concerned. So I can remove constants from that sum. What I'm going to do is I'm going to remove the constant 3 over n from the sum, but I'm not going to remove it from the limit. The reason I'm not removing it from the limit is we are taking the limit as n approaches infinity. So with respect to the limit, n is not a constant, but with respect to the sum, it is. So I'm going to remove that. It'll make the sum a little bit easier to evaluate. 3i over n cubed minus 6 times 3i over n. All right. And now it's about making this look a little bit nicer. So I've actually cubed that first expression here, and I've multiplied the 6 by this term. But now what I'm going to do is use some of our summation laws that we originally were using earlier on in this unit to clean things up here a bit. I can look at this whole thing as the sum of this difference, or I could look at it as the difference of two sums. So that's the next way that I'm going to write this. And so now at this point, I could and probably should remove as many constants from these individual sums as I can. So I'm taking the limit as n approaches infinity of 3 over n times this whole expression, but I'm going to take this constant 27 over n cubed out of that first sum, leaving behind an I cubed. And I'm going to take the constant 18 over n out of that second sum, leaving behind an I. And those are constants because in each of these sums we are plugging in values for I, not n, up until we plug in n. So n is a constant in each of those sums. And now I can actually look at this 3 over n as something that I could distribute into each of these terms. So you'll remember, if we go back to our original rules that we were using for evaluating sums, we've got a couple here that hopefully we remember, but if we don't, we could look back in our notes at this point, and we know what these expressions equal because we've been able to boil these down to expressions that we're familiar looking at. So I still have the limit as n approaches infinity of, and I'm going to say 81 over n to the fourth, but instead of writing the sum of I cubed from 1 to n, I'm going to replace that with an expression that I know it is equivalent to in n times n plus 1 over 2 squared minus, and I still have 54 over n squared, but I'm going to replace this with n times n plus 1 over 2, and this just goes back to those sum laws that we had at the beginning of this unit in Appendix E. So in the next step, what we want to do is simplify this as much as possible by separating each of the components. And in the interest of time, I'm skipping ahead and not writing it all out in front of you. But remember that this 2 right here is really a 2 squared, so that's really a 4. And rather than writing this all as one fraction bunched together, we're splitting it apart and we're getting a bunch of different fractions that we can rewrite like this. So I can put the 81 over this 4, and I can take one of these n's, because it's really an n squared, and put it over one of these n's. And then the other one of these n's, put it over another one of these n's. And then these two n plus 1's are their own numerators over individual n's. And I've done a similar thing here and just separated all of these components. And so that makes this limit a lot easier to evaluate because some of these expressions are pretty simple. N over n is 1, n over n is 1, n over n is 1, and then we've got an actual value that'll arise from some of these other numbers. And so now at this point, we can evaluate this limit, and we can say what is going to happen as each of these n's approach infinity. We'll say in this first case here, we're still going to have 81 fourths, but that's going to be times 1, essentially, right? Because if that number is approaching infinity, then this part of the expression is approaching 0. The same thing is happening here. So times another 1 minus 27 times 1, because we've got that same situation there. And so what this really amounts to is 81 fourths minus 27, which if we calculate that is negative 6.75. So what we should think about is, why is this number not the same as the number that we got in the last example? Because when we did this with a Riemann sum with 6 intervals, we had negative 3.9375, but that is a smaller number than this. And the difference is that this is calculated with the limit of n as it approaches infinity, and this is with 6 rectangles. So obviously this is a more accurate number because we calculated this assuming that we have infinitely many rectangles that we're calculating.